question in the chat box. Um, Let us continue. The recording is in parts, so I've just recorded the first part just now. I'm going to start recording the next one. Okay. So far, what we have done in the first half of the um today's lecture, right, or today's meeting, is basically just looking at some of the more of like refreshing back the important tools that we use, right, in basically that we learn in mathematical economics. And we have a look at the optimization of a single variable function, and also optimization of multiple or more than one um, variable, right? And basically we're going to deal with functions with several variables, and also um, I would say in particularly in looking at consumer and also producers behavior, right? We're going to deal with this constraint optimization, right? It's either maximization or minimization. So we have look at how to or what are the conditions, right, that must be fulfilled in order for us to find an optimal point if we are looking at a function with several variables. Now, in looking at the consumer optimization problem normally, right, or as an example, just like the first paper that we saw just now, um, where consumers utility, that is a function of consumption and other stuff, um, is basically, and also it's actually being maximized subject to certain constraint. So normally it's going to be a budget constraint lah. So in our case, in the case of a consumer's problem, right, and a consumer optimization problem will lead to the derivation of a demand function, right? And we know that the definition of demand is basically, you not only uh, uh, willing but also able to buy, right? So we talk about effective demand, right? So that willing is coming from your, consumer's utility or preference, and able is coming from the budget constraint. Okay, so that's why we say that it must not only, you want to buy it, but also you must be able to buy it. So that's how we define demand in our undergraduate courses, right? And then we know that how does it's actually represented, or where basically that is coming from, is basically coming from the this constraint optimization problem of consumers utility, right? So we have the utility as the objective function, and budget constraint as the constraint, right? Budget function is the constraint, and uh, that's, I think, well, without learning economics, people would understand that, right? So you have that you want to consume X and X1 and X2, right? In order for you to maximize your utility, but how much that you can consume will be determined by how much income that you earn. And that put aside, of course, we have a model where we look at current consumption and future consumption. That's when we are looking at the one of the input markets, what do you call that? The capital market. Okay, so we put aside that one. If you're looking at one period, just like we want to maximize the utility now, right? By choosing two goods or three goods, then of course, if there is no constraint, then people want to consume as much as possible. given their utility function, right? But then, of course, there are limitations that we need to take into consideration when we are examining the consumer's behavior. Okay, so the value that means that put the combination of x's. If you're talking about, there are x1 and x2, then these are all the combinations of x's in which we can consume, right? Into two sets of this combination of x's, right? So the first one is feasible one, the one that is still within your budget, and the other one is, of course, the non-feasible one where it's over or beyond the budget constraint. So if we have what we call that the limitation, right? And then there are certain combinations of access that is available but is not feasible for individuals to consume. Okay, so when we talk about consumers utility maximization problem, then of course we are looking at when we say X, then these X's are basically the goods that is or basket of goods that is feasible to the consumer. Okay, so the value of X may all have to be greater than zero, right? And also consumers' choice limited by the amount of the purchasing power available. That is, in our case, that's the budget that they have. So we have the Lagrangian multiplier method, in which we take into consideration the constraint into the optimization problem, right? So without the constraint, we can directly or straight away solve for or find the first order condition, right? First derivative of the function with respect to the choice variable and solve them. But then since there is a constraint, or there might be a case where we have more than one constraints, right? Then we have to take into consideration all of these constraints, right? So Lagrangian multiplier method is a way that we can, we can solve the or constraint optimization problem. So we have this objective function y. Let me use my laser pointer, right? So we have this y as the optimize the budget, the objective function, right? And we have the constraint here g, which are also a function of x1, x2 until xn. Okay, so you can imagine that this is a utility and the budget, right? So normally it's going to be u is a function of x1, x2, in this case until xn. So you can take any this is a general form, so you can take a specific form. And then if we're talking about a specific form, for example, let's say the easiest one is x1 alpha, x2 beta, and so on, right? And then we have the budget constraint. So we have the income of the um, consumer, right? And then that's going to be P1 X1, P2 X2, um, and so on until N. Oops, okay, no need of this. All right. So that is, of course, commonly a common constraint that we will see a lot of times when we are examining individuals' behavior. Okay, so how do you going to incorporate this into the optimization problem is by forming the Lagrangian function, right, which is the function of the objective itself and also the constraint. Okay, and and we have the Lagrangian multiplier lambda here, right? So lambda here is called Lagrangian multiplier, and the way we're going to solve this is again follow the same procedure, that is to find the first order conditions for the Lagrangian expression, or for the Lagrangian function instead of the objective alone. Okay, so first order condition generally the same as um, the first order condition if you're looking at a function with multiple variables, right? So we have dl dx1 equals to 0, dl dx2 equals 0, and so on. Or maybe you can write as 1 L1 0, right? Or L2 0, and so on until Ln. Okay, right? Some students ask me which notation that they should use. I just say that it's up to you on your own. If you are comfortable with the LDX1, then use it. If it's L, subscript 1, then use it. Or some student use F, if it's F prime 1, something like that, right? So it's up to you, whichever that you are comfortable with. Now, again, we have all of these first order conditions, and also since we have lambda, then we also have to differentiate L with respect to lambda, and then that also equate to 0. Okay, right? Um, and if we are looking at the lambda that we have incorporate here or included in our Lagrangian expression, right? So we might want to know also what is the economic meaning of lambda, right? Because it's everything that we put in our not regression, the function here, right, should have some economic meaning, right, behind it, right? So that's is basically looking at the impact of change in the constraint on the objective function, right? So that's the what is a function of lambda then, right? That is looking at what is the impact of change in I here, because I some amount of income that we have, because this is basically fixed, right? For example, 10,000 that we earn every month, then we spend it on X1, X2 until Xn, right? All of the list of our basket of goods, and then that with given P1, P2, and until Pn, then we will determine how much of X1, X2 until Xn that we want to consume in our basket of goods, right? That will maximize our utility. Okay, but what if, for example, uh, uh, the impact of increase in, let's say, or decrease in income, right? And how that will basically change the objective, the optimal utility, then could be what you call that, evaluated by looking at lambda. Okay, on Snyder and Kelson, they put it more on the cost and benefit kind of measure, right? Where lambda is basically uh, the all of the um, first order condition here, right, with respect to the objective function differentiated with respect to x1, right, divided by the differentiation of the constraint with respect to x1, right, and so on. All of this must be equals to lambda. And if you're talking about utility function, right? So this is actually U1, right? Or U prime, perhaps, more of that. And also, you're talking about the differentiation of the budget constraint with respect to, I'll just use U1 here. Okay. And that will be P1, right? And so on. So U2, P2, and so on. Right. So it is more of like a marginal utility per dollar, which is the condition that is, if you have an economics at your undergraduate level, you must be familiar with this condition for utility maximization, right? And what it says is that all of the uh, extra access consumed, right, by the consumer um, must have similar, what do you call that, a cost and benefit, right? Otherwise, if one axis give more benefit than the extra cost that it should spend on consuming one extra more X, then the allocation should change. So that means it's still not at the maximum level of utility, right? So that means utilities can still be increased by reallocating the budget to one of the axes, right? So that's how Snyder and Nicholson look at the Lagrangian multiplier, right? It is more of the looking at the benefit of consuming an extra X and also the cost of consuming the extra X, right? But it can also be seen as what I said just now. What is the impact of change in the constraint, right, on the objective function, right? Okay. So that's the Lagrangian multiplier, the optimal axis. At the optimal axis, the ratio of marginal benefit to marginal cost should be the same for every x I. So just like this one, right? The conditions that we have here. Okay. And lambda is common cost benefit ratio for all of the x's, right? So that is the value of the benefit to cost ratio of all the x's here. Okay. Um, so we have also a situation where constraint is not binding when lambda is equals to 0, right? That is, course, if it's 0, then this drops out, right? So that means we are not basically looking at a constraint optimization problem. All right. Um, and in solving for a constraint optimization, then it is uh, you know um, if you're looking at maximization problem, right, then there always going to be a dual problem for the maximization, that is something that is going to be minimized, and minimizing that function or that minimization problem, constraint minimization problem, will yield the same results as if we are solving the constraint maximization problem. So that's always going to have this dual problem in the constraint optimization, right? So we have, but all of these have economics meaning, and also the importance of, you know, uh, linking the two, right? And especially in doing empirical work, maybe um, we want to solve for utility maximization problem, and at the same time, I think we sometimes also want to look at the budget minimization problem. Okay, so if you're looking at firm optimization problem, so we have profit maximization, and the dual is the cost minimization problem. All right, so we'll look at that. I think maybe next week, right? Where we have um, if we have the maximization problem, and we have sets of demand functions that we can derive from there, and if we use the budget minimization problem, and then there's a different set of demand functions that we derive, but both of these demand functions would have there's a way to link these two, because of course, because of this duality. All right. Okay. So In the constraint minimization, the focus is on the constraint. Uh, that is, the constraint will become the objective function, right? And the objective function from the maximization will become the constraint, right? So we have maximization of utility, right, subject to the budget constraint. And we have the minimization of the budget constraint, and it's since it's become objective, right? So we drop the constraint, so become minimization of budget subject to the utility. Okay, so see that these two solving this will give us sets of demand functions, right? Where with different what do you call that arguments, right? And this will be a demand function with rest that will be a function of prices. So we have two axes, P1 and P2, and income. Okay, and also we are minimizing the budget. My apologies for all of this disruption. And we're going to have a demand or demand functions if you have two axes, or more than that if you have three demand functions, if you have three axes and so on, and that's a function of prices and utility. Okay, so note that the only difference here is the third arguments there, that is income or utility, depending on which one that we solve, right? And then we have a nice way to show that how these two are related to each other, right? And of course, we're going to see how to derive one from another and so on, right? And so similarly for profit maximization problem, right? When we have profit maximization and also cost minimization, right? So we're going to see derive still demand function, right? But this time it's demand for input, and we will see differences, the same, almost the same difference in terms of the functions or the demand input demand functions that we derive from both problems. Okay, profit maximization and also cost minimization. Um, and here, that is what is written here. Individual maximize utility subject to budget constraint. A dual problem is individual minimize expenditure, but needed to achieve a given level of utility. So in this case, utility is held constant. In this case, the expenditure is held constant. And then firms minimize costs of inputs, reduce the given level of output, right? Or the dual problem is firms is trying to maximize the output for a given cost of inputs purchased, and we can see that this can be achieved by directly solving for the firm's profit maximization problem. Okay, right. So in one of these, maybe a bit this is what I found last time, a bit confusing for the students, right? When to use a constraint and when to not use a constraint. It's actually a constraint optimization, but because we can substitute the constraint into the objective function, then it simply become uh, a non-constraint optimization. And I think this is the final one where we have homogeneous function and also homothetic function. Saya apa? Ni ke? Yes. Oh, okay. So homogeneous a function f is a function of x1, x2, xn, right? Is said to be homogeneous of degree k. So normally we I think we're familiar with what happens if all the variables, or all the endogenous or independent variables, right, is double, for example, right? And what happened to the value of the value of the function itself? Okay, so I think we are familiar with um the increasing return to scale, decreasing return to scale. So it's something related to this homogeneous function, right? That is, in this case, we say that if it's homogeneous of degree k, if all of the x's here, right, are multiplied proportionately, right? So that's important, right? Proportionately increase. Let's say that initially we consume one plate of rice and one cup of coffee, right? And what happened if we increase proportionately? That means double the price and also double the coffee. So what happened to the utility, for example, right? So that is if it is increase, right? With the rate of k here in this case, right? Then it's a homogeneous of degree k. So it can be homogeneous of degree some degree here. So k can take uh some value, 0, 1, 2 maybe, right? So what is important here is if we double all in the axis here by t, right, then the function itself increase by k. Okay, so if it's equals to 1, doubling all of the arguments doubles the value of the function itself. If it's 0, then double all the arguments will leave the function unchanged, right? Because this is basically t as a function of t as a power of 0. Okay, um, so a function that we normally use is the Cobb-Douglas function, for example, right? So we have uh let's say y right now x to the power of alpha and y to the power of beta. Right, and we say that if this is need to put that f macam kat atas so that we don't get confused. So f x y and f tx ty is basically tx tx alpha t y beta, right? And then that will be t alpha plus beta x alpha y beta, right? And then that will be t alpha plus beta f x y, because this is the original function, right? And that means here this Cobb-Douglas functions is a homogeneous of degree alpha plus beta, right? So if you have x f y equals to x 1 x1 tak payah tulis 1 kan 2 lah senang alright 2, and that means y2, sorry, right? So that means this is a homogeneous of degree 4. Okay, but normally we have homogeneous of degree 1 lah so that is if it's f x y x to the power of 0.5 y to the power of 0.5. So it become what we call that this function is homogeneous of degree 1 because it's 0.5 plus 0.5. Okay, and finally we have this homothetic function, right? It's actually a function where we take the monotonic transformation of homogeneous function, and it's noted by sorry Snyder Nicholson, right? That uh, the homogeneous function is also a motetic function because of the limitation in terms of the way we can basically take a monotonic transformation. Okay, so but what is important here is that uh, the for homothetic function, right, when we take a monotonic transformation, then it basically preserve the feature of the original function. So what is important when we examine um, consumers' behavior, for example, right? And when we solve for utility maximization problem, then we're going to have to look at the one important condition is the uh, margin rate of margin rate of substitution be equals to the ratio of prices. And margin rate of substitution is basically the ratio of marginal utilities, right? And if we have a specific function, that's going to be ratio of the axis, how the arguments or how the independent variables of, right, are related, right? So x1 over x2 over x1, for example, a common margin rate of margin rate of substitution. Okay. Um, so when we look at utility function, right, it's basically represent some preference, right? And when we see preferences, we don't have a specific function, kan? Uh, the only thing that we have is the order of preferences. So I prefer what do you call that? I prefer one brand over the other, for example, or I prefer perhaps X1 over X2, the simplest, the simplest uh, uh, basket of goods that we can come up with, right? X1 and X1 over X2, for example, right? But there are many ways of showing this in a specific function, right? But what is more important is that however we represent that using a utility function, then it must preserve that relationship between the two axes, right? So it must preserve the same order of preferences. So that's why I think, that's why we say that in most of the time, of course, we deal with homothetic function, right? And the monotonic transformation, because the monotonic transformation then will not basically change the order or the trade-off of the two axes that we are going to examine. Okay. Um, what else did I have here? Nothing. Right. So while when learning microeconomics or even macroeconomics or any other advanced level, even the elective courses, right? So we will always going to be blended with mathematical what do you call that approach, a quantitative approach, right? So this is just how do we make fun of economics, right? So it's actually you know sometimes we don't know whether we are looking at or studying mathematics or economics, right? So then you say that if it's the question, if did you learn anything useful? So if you said no, right, I seriously doubt that it's anything usable, then you say that it was economics. Right? So this is just making fun of economics, right? Now, if there any question, I will take it right now. And questions so far? Okay. Anything? I don't see anything from the chat box. Ada soalan ke? maybe we can stop right now so that we still have time for our Muslim friends to go perform prayer. Izani ada soalan? Iziani? I see Joanne. Jiawe, anything? Malati?
Doctor,
Nora?
I have a
Yeah.
question. Sorry.
Yes, yes.
Doctor, all these functions that you've gone through with us, we're gonna revisit all of them as we go through the chapters, right?
We going to use them actually.
Yeah, we're gonna use them as we go along. Yeah.
Yes,
Okay.
yes. Yeah. So
Okay.
if you're not familiar with some of the optimization rule, I mean the derivative rule, maybe you want to look at or refer to some books.
Okay. Okay.
Yeah.
Yes.
Okay.
I do.
Right.
Thank you.
You're welcome. Okay. Anything? If none, then we can end our meeting here.